Hello, I'm Jérémy Ledan. I'm currently a postdoc at the University of Strathclyde, and I'm going to present my brief announcement about approximate agreement tasks on graphs and simplicial complexes. So the main topic of my talk is this task called graph approximate agreement, where we fix a graph G, and every process is given as input a vertex of this graph. After communicating, each process should decide on an output vertex such that the following conditions are satisfied. Agreement says that the set of outputs of all the processes should be a clique of the graph, and validity says that if the set of inputs is already a clique at the beginning of the computation, then every output should be within that clique. So to avoid confusion, notice that the graph G has nothing to do with the computational model that we use to solve the task. G is only here to specify what combinations of inputs and outputs are allowed by the task. So what do we know about this task? Novak and Rybicki showed that in the Byzantine setting, the task is solvable whenever the graph G is chordal. So here is an example of a chordal graph. Castaneda and others showed that the task is not solvable when G is a cycle of length at least 4. And more recently, this paper by Alistair and others shows that the task is solvable when G is a nicely bridged graph. So here is an example of a graph that is nicely bridged, but it is not chordal. And they also show that the task is not solvable when G admits what they call a lower bound labeling. So what this says is basically that the graph should have some empty cycle and possibly some stuff around it. To sum up what I just said, there is the class of chordal graphs and the class of nicely bridged graphs, where the task is solvable. And for cycles and graphs with a lower bound labeling, the task is not solvable. So here is an example of a graph that doesn't fit into any of those characterizations. So currently it is not known whether the task is solvable or not for this graph. I will come back to it later. So here my goal is not to improve on those solvability results. It's to show you a new point of view on this graph, which is more topological. And to do that, I will replace the graph G by a simplicial complex. The point of doing that is that I think it gives a better understanding of the task. And I will use this intuition to conjecture the exact class of graphs for which I think the task should be solvable. So first I need to define the complex of cliques associated with a graph G. So fix a graph G, and I'm going to define kappa of G, which is a simplicial complex, whose vertices are the vertices of the graph, and the set of simplexes is defined as follows. Every clique of the graph G is a simplex. So for example, if we have this graph here on the left, and we apply kappa, what happens is that every triangle will be filled by a two-dimensional simplex. And here at the bottom, you can see those 4 vertices that form a clique. They will be filled by a tetrahedron, which is a 3-dimensional simplex. For this other example, once again, the triangles are filled, but this cycle in the middle remains empty because it is not a clique. And finally, for this graph that I showed you before, every triangle inside the graph will be filled, but notice that there is also this outer triangle that is also a clique. So there is one additional simplex, and in fact what we obtain is this icosahedron, which is a triangulated sphere. And what this shows you is that moving from a graph to the complex of cliques of the graph uncovers some geometric information, some higher dimensional topology. So now that we have a simplicial complex, we can consider the following tasks that I call simplex agreements, where the inputs and outputs are vertices of the simplicial complex. But now agreement says that the set of outputs should be a simplex of K. So if you compare this with the definition of graph approximate agreement, you will see that the only difference is that I replaced the word clique by simplex. So graph approximate agreement on a graph G is actually the same task as simplex agreement on kappa of G. So this gives a new point of view on the same task, which is now topological because it's about a simplicial complex. So kappa of G comes with the notion of dimension, and the dimension of this simplicial complex is equal to the clique number of the graph minus 1. So with this equality in mind, we can compare those two results from the literature. First, the one of Novak and Rybicki, who showed that graph agreement in the Byzantine setting is solvable whenever this inequality holds. And in the continuous case, Mendes and others showed that multidimensional approximate agreement in R to the D is solvable in the Byzantine setting whenever this inequality holds. So if you compare these two, you will see that they are very similar, and it looks like the dimension D of the space here behaves very much like the clique number of the graph. So this seems to validate this formula up here that says that the clique number actually is the counterpart of the dimension for multidimensional approximate agreement. So this is the main takeaway message here, that the graph approximate agreement task should be regarded as a higher dimensional task. It's the discrete counterpart of multidimensional agreement. So let's push this idea further and look at this theorem of Herli and Chavit, who showed that multidimensional approximate agreement is unsolvable whenever the space that we consider may contain holes. And by analogy with that, I conjecture that simplex agreement on a simplicial complex K is solvable if and only if K is contractible, which means that it does not contain any hole of any dimension. In particular, this implies that graph approximate agreement on G is solvable if and only if kappa of G is contractible. So let's look at this conjecture on this picture. It says that the class of all graphs where the task is solvable, depicted in green here, is exactly the graphs whose complex of cliques is contractible. In particular for this graph, where, as I said, the status is currently unknown, it's an open question, I claim that this should be unsolvable. And the reason is because, as I showed you, the complex of cliques of this graph is a triangulated sphere, and the sphere is not contractible, it has a hole in the middle. And in fact, any triangulation of a sphere will give you another example of the same kind. The simplest one is this one at the bottom, which is the graph of an octahedron. One last application of this topological point of view is about this lower bound labeling condition. What I claim is that this is of a topological nature. What this says is that kappa of G, the complex of cliques, is not simply connected. For example, if the graph is a triangulated torus, which has a hole in the middle, then we can draw a cycle around this hole that cannot be contracted, and this cycle will allow you to build a lower bound labeling. So this is not proved yet. The implication from left to right is easy to prove, but the other one I didn't manage yet. So this is all I had to say. Thank you for listening to me.